Okay, so we're going to teach on finding an area under a bounded region. So first, let me draw this graph. So we have, we're going to use the Cartesian plane. So first we have the y-axis. And we also have, of course, the x-axis. We have 1, 2, 3 over here. And another 3 right there. So let's say we have this graph. Something that looks like this. Okay. So we can see that the bounded region here is this part. Now by simply looking at it, we can already see that it looks like a triangle. And we all know that the area of a triangle is 1/2 base times height. Now by looking at the graph, we can actually see that the base is 3 and its height is also 3. So knowing this, we can immediately write the area of the triangle. So we have 1/2 and we know that the base is 3 and the height is also 3. So if we solve for this, we have 9 over 2 or 4.5. Okay. But actually, using calculus, we can solve for the same thing. Let's say we have a function that looks like, a graph that looks like this. Okay. So we have this one, this one. So we can also look for an area using an integral, because an area is equal to the integral of f of x from a to b. Okay. So we can actually use this concept with the same graph or the given set of lines for the region. Okay. So if we use it, use integral of the function, and we know that the function here, sorry, I forgot to write it, is actually y equals x. So if we write the function, which is x, and it says here, we should write the boundary or the range, and for this graph, we can see that the range is from 0 to 3. So dx. So if you solve for this, it's actually x squared over 2 evaluated from 0 to 3. Okay, so let's just simplify this. Over 2 minus, we also plug in the 0, of course. Okay. So if you simplify this, 3 squared is 9 over 2 minus 0 squared, and we know that if the numerator is 0, it's automatically 0, so we don't write it anymore. So it's also 9 over 2 or 4.5. So we can see here that the result is the same whether we solve it using this formula or using this formula. I'm going to show another example for looking for an area under a curve. So let's say we have the region having the curve of y equals negative x squared plus 4x minus 1. And let's say it's also bounded by x equals 1 and x equals 3. So if we draw its graph, it will look something like this. First, just by looking at this equation, we can already see that it is a parabola opening downwards. So we can draw it like that. And we have x equals 1 and x equals 3. So we also draw it. And we can see that the region is this part. Now, as we discussed earlier, we can look for the area by looking for the integral of the function. So let's do that. We will look for the integral of the curve, which is the function of negative x squared plus 4x minus 1 dx. And we know that it is bounded by x equals 1 to x equals 3. So if we perform the integral, we can write it as this: negative x cubed over 3 plus 4x squared over 2 minus x. And since it's a definite integral, we will evaluate it from 1 to 3. And for evaluating it, we simply plug in the values. First, 3. So negative 3 cubed over 3 plus 4 times 3 squared over 2 minus 3. And we subtract the second value which we plug in. So we have negative 1 cubed over 3 plus 4 times 1 squared over 2 minus 1. So there. So if we simplify it, we have 3 cubed, which is, and it's negative. So you have negative 27 over 3 plus 3 squared, which is 9 times 4. We have 36 over 2 minus 3. And we solve for the other part. So we have 1 cubed and the negative of it. So negative 1 over 3 plus 1 squared times 4 over 2 minus 1. So if we simplify this further, we have negative 9 plus 36. I'm sorry, this is 2 from here. So you have 36 over 2, which is 18 minus 3. Minus this part, which if you compute for this, this is 2/3. Now if you simplify this again, negative 9 plus 18, this is 9 minus 3, so we can write it as 6 minus 2/3. Or if you solve for this, we have 16 over 3, or which can also be written as 5 and 1/3. And this is the area of the region there. Okay, this time we're going to show you how we look for an area that is bounded by two curves. So let's say this is the first curve, f of x, and this is the second curve. And it is bounded by A and B. Now to solve for this, we can also apply calculus and use the integral of f of x minus g of x. As you can see, it is basically the top function minus the lower function, or the top curve minus the lower curve. So let's provide an example. Let's say we have the region that is bounded by the curves y equals x squared minus 4x and y equals 2x. Now by graphing this, it will look something like this. This is the x-axis, this is the y-axis. If we have y equals 2x, that is basically a line. It will look something like this. And y equals x squared minus 4x, this is a parabola, so let's assume it looks something like this. But of course, we don't know the points of intersection. So in solving for the area of that is bounded by two functions or curves, we first have to solve for the points of intersection, or the POI. To do that, we equate the two curves. So we have the first curve, which is x squared minus 4x. And we equate it to the other curve, which is, in this case, 2x. And we can change its form. We can do it as x squared minus 4x minus 2x equals 0. Or if you simplify it, it can be written as x squared minus 6x equals 0. Now if you change its form, it can also be written as x plus 0 or times x minus 6 equals 0. This is basically the same. So if we have this, we can solve for x. X can be x equals 0, or it can also be x equals 6. So we can use these values and plug it in any of the two functions. So let's say if x equals 0, we can plug it here in y equals to x. So it will be y equals 2 times 0, which is 0. So let's do that. If we have x equals 0, that is the first point of intersection. It's x equals 0. So the first coordinate is of course 0. And to look for its y, we can plug it in any of the equation. So 2 times 0, since x is 0, is 0. Okay, so we found the first point of intersection. And we can also look for the other point of intersection, which is x, using x equals 6. So we can already solve for this point here. We have 6 as its x value, and we can plug it in any of the functions. We can use y equals to x. So if we use x, 2 times 6, since 6 is the x, that is basically 12. So now we know the points of intersection, this one, to look for the area bounded by two curves, using the integral of the top curve. In this case, this is y equals 2x. So we have 2x here. And it says minus the lower curve. And in this case, we're using x squared minus 4x minus x squared minus 4x. And of course, dx. And now that we know the points of intersection, we now also know the boundaries. So in this case, it's 0 to 6. So you can write it there. Now we can apply the integral. So we can actually simplify this first to x squared, 6x minus x squared dx. So now we can apply the integral, and we can write it as 6 times x squared over 2 minus x cubed over 3. And since it's a definite integral, we have to evaluate it from 0 to 6. And to evaluate it, first, of course, we plug in the first value, which is 6. So 6 times 6 squared over 2 minus, we plug 6 here, so it's 6 cubed over 3. So this is the first part. And we should actually subtract it to the value when we plug in 0 here. But in this case, if we plug in 0, it actually amounts to 0. So we don't have to write it anymore. So let's simplify this. First, we can divide this already. So 6 over 2 is 3. And we write this. 3 times 6 squared minus 6 cubed over 3. Okay. So let's simplify this further. This is actually, when you compute it, it's 108. And this is when we perform this 6 cubed over 3, it's actually 72. So if you simplify this again, this will actually amount to 36. And that is your final answer. So we can use the formula to look for the area that is bounded by two curves. And 36 is the answer in this case.